Hello, my name is Carl Chick and I work for TRW Automotive as a systems software architect, supporting multiple product lines such as electric steering, braking and occupant safety systems. A key element in the design of these product lines is an electronic control unit, otherwise known as an ECU. A critical stage in designing an ECU is the partitioning of the ECU into hardware and software functional elements, an activity we refer to as ECU architecture design. In this presentation, we shall explore an approach to architecting an ECU using SysML that has been successfully introduced at TRW. There are many challenges faced when developing an ECU. Some typical issues seen across the automotive industry are electronic engineering developing and building ECU designs before safety and software engineering are ready. A lack of formal records kept of the ECU design decisions or derivation from the system requirements. ECU designs that are difficult to refactor, resulting in software fixes or safety compromises and concessions. Architectural changes that result in a redesign of the ECU through a next generation ECU. And increasingly, with globalization of companies, teams that are split across different geographic locations, often whole engineering disciplines, leading to poor interdisciplinary communication. Think about your own projects. Who decides what should be implemented by hardware versus software? What assumptions and decisions have they made? Were they best placed to make those decisions? Was the impact of safety on the ECU design considered at the beginning of the project? Did you have a suitable block diagram of the ECU design to support the safety case? If you answered no, or not sure to some of these questions, then you have already experienced the problem. But how can we address these issues? The solution is simple. Everyone works with a common view of the ECU that we call ECU architecture. This allows us to capture and document a common understanding of the ECU design that is used for all hardware, software and safety development activities. It enables us to satisfy the needs of all the stakeholders of the ECU, not just the functional requirements. It considers the impact of safety up front and enables us to address the needs of ISO 26262 and Automotive SPICE. The approach aims to capture what is in people's heads, such as goals or concepts, by defining those thoughts using the language of SysML. This enables multiple people to have a common understanding. By integrating the ECU architectural work of all the engineering disciplines into a common point of reference, we can ensure that the ECU architecture provides a unified view that addresses the demands of all the engineering disciplines. The overall key benefit of this approach is the structured collaboration between hardware, software and safety disciplines. What exactly do we mean by ECU architecture? Well, before you can design hardware and software for an ECU, its functionality has to be segregated into hardware and software elements, whilst taking into account any safety concerns. This activity we are calling ECU architecture design. To be successful, it requires the collaboration of hardware, software and safety engineering disciplines, and to be coordinated by an ECU architect. The ECU architect's role is to orchestrate the involvement of the different engineering disciplines in developing the ECU architecture, whilst ensuring architectural best practices and concerns are addressed. A SysML model of the ECU architecture is developed, shared and used by all the different engineering disciplines and stakeholders. Hang on, what is SysML? SysML is short for Systems Modeling Language and is an extended subset of the Unified Modeling Language known as UML. SysML is not a methodology, it is a graphical modeling language developed from UML to support systems engineering. We adopted SysML for the ECU architecture methodology as it provides excellent and very relevant modeling constructs that support modeling of an ECU architecture. In this presentation, there are references to some of SysML's diagrams. For a full explanation of SysML and its diagrams, a review of the object management groups SysML tutorial is strongly recommended. This can be found on their website. Back to ECU architecture. There are two distinct points where the ECU architecture design and the functional safety life cycles interact, which I've labelled as ECU functional architecture and ECU safety architecture. The functional architecture models the functional needs of the ECU and is subsequently used for the functional safety analysis that lead to the definition of the ECU's technical safety requirements. The ECU safety architecture uses the technical safety requirements to enhance the functional architecture with any additional safety measures that are required to ensure the ECU's design is safe. We shall look at each of these two steps in turn. The first step is ECU functional architecture and is split into three phases. System level analysis aims to elicit the problem domain from the stakeholders of the ECU using use case analysis. Logical architecture aims to ensure the problem domain is understood correctly by defining its logical structure and behaviors, in other words, what the ECU has to do. And lastly, physical architecture, which aims to model the solution domain by defining the required structure and behaviors in terms of hardware and software elements, and that is how the ECU shall be partitioned. The functional architecture design is use case centric and is performed in an iterative manner, use case by use case. The first phase of functional architecture design is the system level analysis, that is, the eliciting of the problem. The system level analysis phase is all about eliciting from the problem domain the context, goals and functions of the ECU. The aim is to define a black box view of the whole ECU that identifies functions that the ECU will need to fulfill. To help visualize this very graphical approach to modeling an ECU, I shall be using a simplified example of a suspension control system where the driver can select stiffer, sportier suspension by pressing a sport mode switch on the dashboard. Defining the ECU context ensures that everyone agrees what is in and out of scope of the ECU. To define the context of the ECU, we first need to identify the people and items that the ECU interacts with. The problem domain is full of elements external to the ECU that it interacts with. For example, the vehicle, the driver, sensors and actuators, battery, other ECUs, onboard diagnostic equipment. In SysML, these problem domain elements are modelled with blocks using a block definition diagram, the green block in the diagram being our ECU. Some elements are people or systems that expect something of our ECU. These are modelled using actors, the little stickmen in the diagram, which we shall come back to in a bit. The problem domain elements are used to define the context of the ECU. In the example shown, you can see the vehicle block contains our ECU, highlighted in green, and the suspension damping valves, sport mode button, and a couple of other ECUs that our ECU talks to. Flow ports are used to define the interfaces to our ECU. They're the little squares round the periphery of the ECU. These are connected to the external entities using flows that define the flow items that can interact with our ECU. We now have a clear definition of the boundary of our ECU, its external interfaces, and its context within the problem domain. Next, we need to work out exactly what our ECU has to do. So who knows what the ECU needs to do? Well, the stakeholders of the ECU all have their own views or goals of what they want from the ECU, and we use use case analysis to elicit and capture them. The stakeholders of the ECU are anyone or anything that has a vested interest in the ECU, whether it be cost, production, function, usage or constraint. Some stakeholders may already have been identified as problem domain elements, but it is important to identify all of the ECU's stakeholders, since they are the source of the ECU's use cases. Actors, the little stickmen in the use case diagram, are used in SysML to represent the stakeholders. Actors can hold information about the stakeholders, such as their contact details, or a statement of what the stakeholder would consider a success criteria of the ECU from their point of view. This helps you to understand the stakeholder's perspective from which you will need to identify their use cases. Be curious and discuss with the stakeholders what they will do with the ECU, and you will often uncover hidden use cases that are not obvious from any written specifications. Try to ensure that the use cases are goal-orientated rather than functions of the ECU. They should read as transactional statements, where the stakeholder achieves something by using the ECU. The stakeholders and their use cases are identified and captured using a use case diagram. We usually tag the use cases using stereotypes to indicate primary, secondary and sub-use cases. Also, to aid planning, it is useful to tag the use cases with a priority. If you have a large number of use cases, you can use several use case diagrams and then put all the primary use cases on a main use case diagram. Use cases describe the usage of the ECU within the context of the problem domain. We need to ensure that we correctly understand the use cases and work out exactly what each use case expects from our ECU. We use an activity diagram to capture the behavior of the use case as a set of activities required to fulfill the goal of the stakeholder. Swim lanes are used to allocate the activities to the problem domain elements. The activities allocated to our ECU are functions of the ECU that are required by the use case being analyzed. The ECU functions are defined as operations within the ECU's own block and have input and output parameters that correspond to the interfaces of the ECU. An ECU use case may consist of one or more ECU function. As well as identifying the ECU functions, it is now possible to confirm with the stakeholder that we have correctly understood their goals. The second phase of functional architecture design is logical architecture, which aims to understand the problem. A problem has to be understood before it can be solved. The logical architecture aims to understand and define the required functional behavior of the ECU functions and ensure that they can coexist harmoniously. This is performed in two steps. First, the functional behavior of the ECU functions is modeled. Next, the functional behavior is grouped into logical blocks that collectively form a unified structure of the problem domain, which is the logical architecture of the ECU. As each use case is modeled, the ECU functions are mapped into the logical architecture. This means conflicts and requirement gaps within the problem domain are readily identified and can be resolved. Keep in mind that the logical architecture defines only what the ECU functions are required to do, not how they will be realized. In other words, the logical architecture is independent of the possible ECU design solutions. In SysML, we model the functional behavior of the ECU's functions using activity diagrams. An ECU function is broken down into a set of atomic activities that are not solution-oriented. The flow of control and information between activities is depicted, and swim lanes are then used to allocate the activities into logical groupings. The swim lanes represent the logical blocks that will form the structure of the logical architecture. The ECU architect uses their architectural skills to select suitable logical blocks. The activity diagram provides an overview of the required behavior that is easily understood and verifiable against the source requirements or stakeholder. Having identified the behavior and some logical blocks, we need to ensure that the ECU function integrates into the overall logical architecture. To do this, we allocate the behavior to the logical blocks and define the interfaces between them. Each activity is realized as an operation of a logical block. The flows between the activities represent the input and output parameters of these operations. Where a flow on the activity diagram crosses a swim lane boundary, it indicates a flow between the logical blocks that represent the swim lanes. A structural view of the ECU function in terms of logical blocks and flows is created using an internal block diagram within the logical architecture. Flows and flow items are used to define the information, materials or items that flow between the logical blocks, as indicated by the red arrows in the example. The flow items are also used to specify the input and output parameters of the logical block operations. The operations of the logical block may represent activities from many different activity diagrams. In other words, some ECU functions will have actions that are common, such as handle and error. The ECU architect ensures that the logical blocks adhere to architectural principles, and as the wider view of the problem domain becomes visible, is able to resolve functional conflicts and identify knowledge gaps within the problem domain. As we iterate through the use cases, the functional behavior of the ECU functions is gradually integrated into a unified logical architecture. We can create an integrated view of the whole logical architecture, since the diagrams in SysML are just that, views into the architectural model. The logical blocks are abstract to any physical solutions and only represent the logical functionality required to perform the ECU functions. The only physical influence is the ECU's interfaces to the outside world, since these are a given solution and not for debate. The logical architecture provides the infrastructure for creating the physical architecture. The third and last phase of the functional architecture design is physical architecture, which models the architectural solution. The architectural solution for the ECU is defined in terms of how hardware and software elements shall be used to fulfill the goals of the ECU. We call this the physical architecture. The transition from problem domain to solution domain is non-trivial and is performed in steps. Engineers are good at solving problems, and the logical architecture defines the problem. So first, we engage the experience and creativity of relevant engineering disciplines to devise a technical design concept of how we can realize an ECU function using hardware and software solutions. Next, the ECU architect models the physical behavior identified by the technical design concept to ensure that there is a correct and common understanding of it. And lastly, the physical behavior is allocated into hardware and software elements in line with the concept, and their interfaces are defined. Let's take a look at those steps in a bit more detail. Each logical activity, or closely related set of activities, is analysed, and if necessary a technical design concept is devised to work out how hardware and software elements can be used to realise the activity. This requires the collaborative creativity and experience of both hardware and software disciplines to conceptualize a potential design solution. At the discretion of the ECU architect, some logical activities may be passed straight through to the solution, if there is clearly no need to partition the behavior, and it can be allocated directly to either hardware or software. The ECU architect holds a workshop and invites hardware and software engineers with relevant experience to help develop the concept. The concept workshop provides an arena free from formal methods within which creative and practical ideas can be freely explored. The result of this discussion is captured and embedded into the architectural model for future reference. The technical design concepts are formalized by modeling them in the physical architecture using activity diagrams. This ensures the concepts are understood correctly by the ECU architect. It provides a clear definition of the concepts for all parties involved and facilitates the mapping of the concepts to hardware and software elements within the architecture. Each logical activity diagram will have a counterpart physical activity diagram, and in each case the logical activities are broken down into a set of atomic physical activities that can be attributed to software or hardware in line with the technical design concept. Some logical activities will be wholly allocated to hardware, some to software, others will be split between hardware and software. The swim lanes are used to allocate the behavior to hardware and software elements within the physical architecture. The diagram here shows how the logical activity control valves is broken down into three physical blocks. There is a software block shown in blue that has the control logic for controlling the damper valves, and there are two blocks chosen to drive the hardware shown in green. One switches the high side and the other drives the low side and samples current flow. If there are additional considerations such as timing and sequences to consider, then these are captured and defined using sequence diagrams. rationale for why a solution is partitioned in a particular way, and any additional or derived requirements are also captured and defined within the physical architecture. While the relationship between the problem and the solution is fresh in the mind, the mapping between the logical architecture and the derived physical architecture is recorded using a requirements diagram. On this diagram, the allocation of the logical operations down to the partitioned hardware and software operations is depicted. The mapping is now visible rather than an unreliable memory, and provides the signposts by which others can navigate their way between the problem and solution domains. The last step is to formalize the partitioning of the design concept into hardware and software blocks and ensure it integrates into the overall physical architecture by defining the interactions between the blocks. Each activity in the physical activity diagram is realized as an operation of the physical block allocated to its swim lane. These operations define the responsibilities for the hardware and software physical blocks. On the physical activity diagram, there are flows between activities that cross the swim lane boundaries. These indicate the interfaces between the physical blocks. Some flows may be reused from the logical architecture, while others are defined within the physical architecture. The flows are used to specify the input and output parameters of the physical operations that represent the physical activities. Internal block diagrams are used to depict the flows between the physical blocks. Flow ports are used to define block interfaces where necessary. For example, we used flow ports to define the microprocessor peripheral requirements. The purple block on the diagram is tagged as a build and is used to indicate a build of software or application. Typically, you might have 2 software application builds per microprocessor, 1 bootloader and 1 application. The interfaces between hardware and software are now identified, and the concept has been integrated into a unified view of the physical architecture. Before we move on to safety architecture, let's recap what we looked at with functional architecture. We start with the problem domain and use its elements to define the context of the ECU. The stakeholders and their goals of the ECU are captured using use cases. The behavior of the use cases is modeled using an activity diagram. Activities are allocated to the problem domain elements, and this identifies the functions of the ECU. The behavior of the ECU functions is modeled using logical activity diagrams. These are partitioned into logical blocks, which are then used to build a unified logical architecture of the problem domain into which all the ECU functions must coexist. The transition from the problem domain to the solution domain is aided by the use of the technical design concept. This is developed with the collaboration of hardware and software engineering disciplines. The behavior of the technical design concept is modeled using a physical activity diagram to ensure that it is correctly understood. And finally, the physical behavior is partitioned and allocated to hardware and software elements, which are then used to define the physical architecture. The ECU's functional architecture provides an excellent input to the functional safety lifecycle. So let's now look at functional safety. Safety can have a major impact on the design and validation of an ECU. ECU architecture plays an important role in addressing safety concerns early in the development of the ECU, as well as supporting validation of the ECU. The second step in architecting the ECU is safety architecture design. This aims to support the functional safety lifecycle by modelling the safety concerns and resultant safety measures of the ECU at an architectural level. The safety architecture design is performed in 3 steps. Functional safety analysis, where we model the safety needs of the ECU. Establishing a safety concept of how the safety needs can be met. And finally, safety architecture design, which then models the solution. The approach is again iterative, but this time operating upon safety integrity functions, or SIFs as we call them. We shall look at each of these 3 steps in turn. The first step of safety architecture design is functional safety analysis, which models the safety needs of the ECU. First, the safety integrity functions, or SIFs as we call them, need to be defined. SIFs are logical groupings of the ECU's technical safety requirements, oriented around similar subject matter or functions. They provide a convenient and logical way to organize the safety architecture work products. SIFs might cover safety concerns such as memory protection, safe communication, or power supply monitoring. SIFs are modeled in SysML as separate entities using blocks, which act as containers within which to hold the architectural analysis conducted during the safety architecture design of each SIF. Each SIF is scoped by allocating the relevant technical safety requirements to it. SIFs break up the safety concerns of the ECU into manageable chunks that can be processed iteratively or in parallel. The most important step in defining a SIF is choosing an appropriate level of safety measure or measures to satisfy the safety requirements. The selection of a safety measure should be guided by your functional safety engineer and the assigned ASIL of the safety requirements and ISO 26262, particularly Part 5 at Annex D, which provides good guidelines for differing levels of diagnostic coverage. An activity diagram is used to capture what the safety measure must do logically, that is, what the SIF functionality must achieve, but not how the SIF will be realized. For example, a SIF might indicate that a windowed watchdog with a separate time base is required, but the SIF would not state that a power supply with a built-in watchdog should be used. The second step of safety architecture design is to establish a safety concept or solution for each SIF. To devise a design solution to the SIF often requires input and collaboration of safety, electronic and software engineering disciplines. The ECU architect holds a workshop and invites hardware, software and safety engineers with relevant experience to help develop the safety concept. The workshop allows the different engineering disciplines to develop a concept with the freedom to be creative in applying their experience to the task. The SIF concept must address all allocated software requirements, taking into account the ASIL of the safety requirements and related architectural elements. The result of this discussion is captured and embedded in the architecture model for future reference. The third and last step of safety architecture design is safety architecture design, which models the safety concept in terms of the solution. The SIF concept is modelled in the physical architecture using an activity diagram. This not only ensures that the SIF concept is understood correctly by the ECU architect, but it also facilitates the mapping of the SIF concept into the architecture. We again use swim lanes to allocate the SIF's behaviour to hardware and software elements within the physical architecture. This may result in the creation of new hardware and software elements, or the modification of existing elements. The activities are realized as operations within the hardware and software blocks that represent the swim lanes. If there are additional considerations, such as timing or sequences to consider, then these can be captured and defined using sequence diagrams. Any rationale for why the concept is partitioned in a particular way, and any additional or derived requirements are also captured and defined within the physical architecture. The last step is to formalize the partitioning of the safety concept into hardware and software blocks and ensure it integrates into the overall physical architecture by defining the interactions between the blocks. The flows that cross the swim lane boundaries on the SIF's activity diagram identify the interactions or interface flows between the physical blocks. Some flows may already exist, others are created as required. The flows are also used to specify the input and output parameters of the physical operations that represent the physical activities. An internal block diagram is used to depict the flows between the physical blocks. The SIF has now been integrated into the overall physical architecture of the ECU. As you have seen, the ECU safety architecture is not a separate work package to the ECU functional architecture, but rather a phase during which the ECU functional architecture is updated from a safety point of view, creating SIF-specific views of the architecture that explain how the safety measures shall be implemented using hardware and software elements. Throughout the development of the ECU safety architecture, there is a need to classify all the hardware elements, software elements and flows with an automotive safety integrity level, or ASIL for short. Each technical safety requirement should have an ASIL allocated to it that was derived during the technical safety concept by safety engineering. Another source of ASILs is from the customer, where they may define the ASIL of specific ECU interfaces, communication signals, or even black box software components. ASILs can be modelled in SysML by applying custom stereotypes to the model elements. This also allows any ASIL decomposition to be depicted within the architecture and its rationale to be captured using rationale comments. Let's recap what we looked at with the safety architecture. Out of the functional safety lifecycle come the technical safety requirements of the ECU, which we partition into safety integrity functions, or SIFs for short. In line with the allocated ASIL of the requirements and guided by ISO 26262, we select suitable levels of safety measures to mitigate the technical safety requirements. The required behavior of the safety measures is modelled in a SIF logical activity diagram. A technical safety concept is developed through the collaboration of the different engineering disciplines to conceptualize a solution using hardware and software resources. The safety concept is modelled within the physical architecture using an activity diagram to confirm a correct understanding of the concept and to integrate it within the architecture. Finally, the partitioning of the safety concept into hardware and software elements is formalized by creating new blocks, modifying existing blocks, and defining the interaction flows. Note that the ECU safety architecture is not a separate work product, but rather a phase during which the ECU's functional architecture is updated from a safety perspective. In meeting the challenges outlined at the beginning of this presentation, we have developed an approach to architecting an ECU that provides the following benefits. Addresses and satisfies all stakeholders of the ECU, not just the functional requirements. Separates out problem domain from solution domain, and so allows reuse of the problem domain architecture across different variants of the ECU. Defines a clear and concise architecture developed to a known standard, and so eases communication across the engineering disciplines. It provides a platform which aids review and validation activities and also supports the safety case effectively right through to product qualification. The approach dovetails neatly into hardware, software and safety development activities, whilst balancing the demands and needs of both Automotive SPICE and ISO 26262. Within TRW, we have successfully implemented this approach on a live product development for a European vehicle manufacturer, and it is now being rolled out to other product lines within TRW. That concludes my presentation on architecting an ECU. Thank you for your kind attention.